So right, I guess we can smoothly start. So dear colleagues, it's my pleasure to introduce you our today's speaker, Professor Alexander Pyatakov from Moscow State University. So Alexander is known as a big expert in magnetoelectric and multiferroic media, co-author of a review on such media, one of the best experts in Russia, I believe. So we were interested in that topic to find out how this is related to axion electrodynamics. And Alexander kindly agreed to give a talk devoted to magnetoelectric and multiferroic media, rich physics behind, and promise for multi-purpose applications. So in case if you have any questions, I encourage you to either raise your hand or type your question in the chat. You may also ask the question by voice, but please make sure not to interrupt the speaker in the middle of the sentence. So Alexander, please, the stage is yours.
Thank you. I would like to thank organizers for the opportunity to participate in this seminar series. And as soon as our seminar is called a theoretical one, let's consider a well-known equation that relate the magnetic and the electric values from a general point of view, from the perspective of symmetry. And we can, we learn school children to check every formula in terms of units. You know, do not add the kilogram to meters, for example, yeah? And it is called dimensional analysis. And I think that every graduate student should make also symmetry analysis of the formula. For example, it's not by chance that the magnetic induction is couples with velocity, for example, and the charge to produce force. And it's not by chance that the special derivative of magnetic field is related to the curl of electric field. So when we talk about magnetic values as a vector, it's kind of oversimplifying the reality, because magnetic vectors are not the vectors in the usual sense, like this pencil. Yeah, this pencil is a polar vector, and it transforms under the inversion symmetry with in this way. Yeah. So when we apply inversion symmetry to the vector, to the polar vector, it switches to the opposite direction. So the sign switches, and of course it is it's invariant with respect to the time inversion symmetry. So you can see plus here. So in other words, it's T even and P odd. But magnetic vectors are quite the opposite. They're just like spinners, yeah. And when the time reversal is applied, it's kind of rewind the film in reverse direction. So when you reverse time, when you apply time inversion symmetry, the direction changes from, for example, clockwise to counterclockwise, and the minus appears in this formula. So under the time inversion symmetry, it translates to the opposite direction, and it's invariant, in fact, with respect to the space inversion symmetry. For example, when you observe the rotating wheel, we can find diametrically opposite points And when you translate them during the rotation of the wheel, the direction of the rotation, I mean clockwise and counterclockwise, remains the same. So it doesn't it's invariant with respect to the spatial inversion symmetry. So in a way, they are opposite polar vectors and axial vectors. In this case, it's magnetic vectors. And they are not usual conventional vectors. And maybe the most vivid example of this is their translation in the mirror. The mirror translation, the mirror symmetry, we can see here that the axial vector reflects, and the reflection is the same axial vector. That reminds me the surreal painting of René Magritte. You can see it here. It's quite unusual. And when the vector is along the plane of the mirror, it transfers, transfers like this, with the opposite direction. So coming back to our electrodynamics, you can see here that the time derivative of magnetic vector, it's not by chance here, because it compensates the oddness of magnetic vector, the T oddness, time. It's not invariant with respect to the time reversion symmetry. Yeah, and you can see here that this time derivative compensated. So minus multiplied by minus gives us plus. And the same is on the other part of the formula. You can see here the special operator, differential operator nabla, and it behaves like polar vector, and multiplied by another polar vector, it gives us a kind of invariant. So we can translate magnetic vectors to electric vectors in this way. So conventional electrodynamics gives us dynamical transformation of magnetic vector to inhomogeneous electric field, and dynamical transformation of electric vectors to inhomogeneous magnetic field. In this way, magnetoelectricity provides a remarkable alternative because magnetoelectricity transforms constant, not always constant, but it can transform also constant magnetic field to the constant electric polarization and homogeneous one, and homogeneous constant electric field to magnetization. And of course, it's not possible in vacuum for the same symmetry reasons, but it is possible in special media that we call magnetoelectrics and multiferroics. When we consider the constitutive relations of for magnetoelectrics, we can see, along with the conventional term that is proportional to electric field, the second term that it's a cross-coupling term that relates electric polarization to magnetic field, and this magnetic field is related by special coefficient that is called magnetoelectric coefficient, and in fact it's a tensor. So there are a matrix. There is a matrix of components of magnetoelectric effects, and the same for the second formula. M is induced by electric field with the same coefficient. In elementary particle physics, the representation is slightly different. we can see here on the right side, it's the so-called axion electrodynamics, and this transformation is expressed in terms of fine structure constant, it's alpha, and a special field that is called axion field, theta, and it's kind of generalization of the case of magnetoelectricity, because in the case of multiferroics and magnetoelectrics, usually these coefficients are constant. But in the case of axion electrodynamics, it's a kind of field theta. So it can also be a dynamical one, and maybe inhomogeneous, and so on.
So, Alexander, I have a question regarding the equations on the left-hand side. I wonder if it is always the case for multiferroics that the coefficient in the first line, alpha and E, is the same as the coefficient in the second line, which you also denote as alpha and E.
It's in CGS system, they're just the same.
But could they be...
System international, it's kind of different.
Yeah, that's clear with the system of units, but I'm wondering, as far as I know, if the medium has some associated losses, then these two coefficients can be not necessarily equal. So at least in this theory of anisotropic media, people sometimes consider that these coefficients can be different, but if they're equal, then we eliminate losses. So could you comment on that, please?
In fact, it's not just a coefficients, it's a matrix. So sorry for some inaccuracies, because if it is tensor, there should be transposed. So, yeah, EG and GE.
Good. Okay, thanks.
Транспонирование. Transposed.
Right. Got it.
But if it's just if isotropic media, in the case of isotropic media, it's just the same coefficient.
Right. Thank you.
Okay. Let's proceed.
Yes.
So when we tell about this coefficient or axion field theta, we should insist that it should be P and T odd. I mean, to relate polar vector with axial one, this is not just a scalar. It's special coefficient that transforms under inversion symmetry with sign reversal, and the same for inversion, spatial inversion symmetry. So we call it P and T odd. And with respect to the combined symmetry, consequently applied spatial inversion symmetry and then time reversal symmetry, it remains invariant. So it's PT odd and P multiplied by T even. It's exactly the definition of the magnetoelectric media that we can find in classic course of Landau and Lifshitz. And in fact, the discovery of magnetoelectric effects started from this point, from the point of publishing this textbook. Because it was published in 1956, and a year later, Igor Zelashinsky proposed chromium oxide as a possible candidate for magnetoelectrics, and Dmitry Nikolaevich Astrov experimentally observed electrically induced magnetization. And in 1 year later, Americans found the reverse effect of magnetically induced electric polarization. And of course, as always happens in nature, there are lots of forerunners that propose this idea of magnetoelectricity. For example, Pierre Curie, our professor in Moscow State University, Boguslavsky, Paul Debye, and Dutch electron engineer Bernard Tellegen even proposed the this special recipe how to produce this media. He proposed to suspend the magnetic particles glued to the electric particles, suspended them in engine oil. He was an engineer, so it was a practical recipe. And as soon as we apply electric field, the electrons orients, and as soon as they are coupled to magnets, the magnets also orients, and vice versa. Magnetic field also can orient these electrons. But remarkably, there were no attempts to make this media until the natural magnetoelectrics were found in 1960s. It was chromium oxide. And in the context of magnetoelectrics, multiferroics are also mentioned. I should notice that multiferroics and magnetoelectrics are not synonymous. In fact, they are independent sets of independent classes of media, but of course they overlap. We can see here the class of multiferroics. It's overlapping of the set of ferromagnetic media and ferroelectric media. And the overlapping set is multiferroic media. So in other words, multiferroics are magnetic ferroelectrics. You see, when we are talking about signet electrics in Russian, yeah, we in English we use term ferroelectrics in analogy to ferromagnetics. So they share the same prefix ferro, and due to this prefix, multiferroics means that the media possess many ferro orders: ferromagnetic, ferroelastic, maybe ferroelectric, and so on. In our case, multiferroics is just magnetic ferroelectrics. So they are called ferroelectromagnets in Soviet tradition, but the new term for them is multiferroid. So how to make the electricity from magnetism, from static electricity, from static magnetism? How to make this magnetoelectricity? There are several recipes, and to complete this quest, we will use the painting of, more precisely, graphic arts of Maurice Escher. It's he's a Dutch, well-known Dutch graphic artist. And he was also well known for his paradoxical prints. And many mathematical ideas are reflected in his arts, or even anticipated. So we start with the concept of antiferromagnet. It's media with two sublattices, at least two sublattices, with opposite direction of magnetization of, with opposite direction of spins. And in what way Maurice Escher anticipated the idea? For example, in 1938, in his lithograph Day and Night, he anticipated the concept of antisymmetry that was later proposed by Alexei Vasilyevich Shubnikov for analysis of magnetic media. For example, it's not just a mirror symmetry. It's mirror symmetry multiplied by color changes. For example, these black birds is a counterpart of this white bird, and they are related by mirror symmetry and also by color symmetry change inversion. So physically, that means that ions are transformed from one sublattice to another with magnetization reversal. It's very good for analysis of antiferromagnets, since there are at least two sublattices, and they are, as a rule, they are related by some symmetry elements. But when we analyze it, for example, chromium oxide, the first magnetoelectric observed, we can find that this inversion symmetry, I point here, relates the sublattices with opposite magnetization. So it's not just an inversion symmetry, it's an inversion anti-symmetry. It's inversion multiplied by magnetization reversal. And we can introduce special order parameter antiferromagnetic vector that is a vector difference, not a sum, but difference of spins. The spin of one sublattices and the spin of ions in another sublattice. So the difference between them, it will be the T-odd vector, of course, because it's composed of magnetic vectors, so it's time reversal odd. And it is also odd in terms of special inversion symmetry, because when we interchange this ion, the terms in this sum also interchange, and the sign of the sum reverses. So L is have mixed nature. It's a polar vector and at the same time axial vector. So PT odd vector, and it can be like a mediator between magnetic vectors and electric vectors, and this combination will be invariant. So they can represent some term in thermodynamical potential. It can be the special energy, magnetoelectric energy. So, and this term means that there is a product of magnetic vectors and electric vectors, and the coefficient that relates them, magnetoelectric coefficients, should be proportional to the components of this antiferromagnetic vector. So when we consider the matrix of magnetoelectric coefficients, every element of this matrix is proportional to some component of antiferromagnetic vector, or maybe combination of them. So the main idea of this slide is that antiferromagnetic vector is a bridge between magnetism, magnetic vectors, axial ones, and polar vectors, electricity. Special case of the antiferromagnetic ordering is it's called toroidal ordering. The at least three sublattices, or maybe even larger, larger number of sublattices. We can see here they form some kind of circle, a moment of the higher order, the higher order magnetic moment. When we observe the curl of magnetization, it's a special moment that is called toroidal one. Why toroidal? Because its field is analogous to the field of solenoid. This toroidal solenoid. So there is a curl of magnetic field and special toroidal moment. So toroidal moment also is a P and T odd vector. And it can also relate magnetism to electricity. Of course, PT odd vectors are not only the toroidal ones or antiferromagnetic. The well-known velocity vector is also PT odd. It relates, for example, in this formula, Coriolis force and the angle velocity, omega. And charge density also is a PT odd vector. And the Poynting vector also is a PT odd vector. That means that it can directly couple to the toroidal vector, so they can form some kind of invariant and some kind of contribution to the energy, and that means there should be special magneto-optical effect that react on the direction of the toroidal moment, and it can be the intensity changes, some kind of dichroism, and in that way, these toroidal domains, the special region area in media that have the same toroidal ordering, these domains can be visualized by optical means. But in this case, it's second harmonic generation, but the principle is the same. Toroidal moment couples to the Poynting vector. So,
so Alexander, may I ask a question regarding this part? So may we anticipate the same coupling of antiferromagnetic vector to the Poynting vector? Looks like symmetry allows this coupling as well.
Could you repeat the beginning?
So previously, you mentioned that this antiferromagnetic vector, which is S1 minus S2, also possesses, it is P odd and it is T odd. So may we anticipate the coupling of antiferromagnetic vector to the Poynting vector, L dot S?
Yes, and the antiferromagnetic domains can also be visualized by magneto-optical means.
Thank you.
As a rule, in second harmonic generation, due to the polar nature of the toroid of the antiferromagnetic vector in this case, and second harmonic generation is sensitive to the electric polarization, to the inversion symmetry break, and also sensitive to the antiferromagnetic vector ordering. So another idea I want to convey is a concept of flexoelectricity and flexo-induced effect. Flexo in Latin means just bending, like this. See, bending of the object, and it's not just in literal means, that means that bending of the object. It can be bending of vector field. For example, this fan-shaped structure of magnetization. The homogeneous vector field of magnetic vectors is just like this, yeah. And when you're bending it, it's kind of fan-shaped structure. It is called spin cycloid structure. So the end of the magnetic vectors can be traced like a point on the rolling wheel, yeah. And you know that the rolling wheel, the point on the rim of the rolling wheel form cycloid arcs, and in case of magnetism, it's spin cycloids. So this is the symmetry analogous between the bending of solid body, the special molecular structure in liquid crystals. They form the same cycloidal ordering for pneumatic director, and cycloidal ordering of magnetization or antiferromagnetic vector. No matter what is the nature of this vector that is bent, the field of this vector is bent. Yeah, no matter what is the nature of this vector, it can be antiferromagnetic, can be director pseudo vector, and so on. So the idea is the same. The idea of bending. When we bend the body, the upper layers are stretched, the bottom layer shrunk, so there is a gradient of deformation, and this is polar vector gradient. Yeah? And the same is for the magnetic ordering. You do not bend the crystal, you bend the vector field of magnetization, but the symmetry consequence is the same. You induce some polar direction, and this is how to make from the magnetic ordering the electric polarization. You just curl it to the cycloid, and mathematically that means that electric polarization is proportional to these combinations of magnetic vectors. There are two terms, but symmetrically are similar. They transforms like a polar vector.
But do I understand correctly that these two contributions enter probably with different coefficients, because symmetry does not restrict?
As a rule, yes. This formula is for isotropic case, of course. As a rule, there should be gamma 1 and gamma 2.
Thanks.
And even more worse, for anisotropic media, there should be some tensors, of course. And it's highly symmetrical sense, just like a liquid. But in fact, this formula is from liquid crystals, but it's very very beautiful one. So we also can use it in magnetism when we neglect the anisotropy.
And then another question. So I would expect that if you write further terms to the polarization, you should incorporate, let's say, second derivatives, third derivatives. So people assume that they are weak somehow. Why they ignore higher order spatial derivatives?
Of course, it's just like an expansion. Up to this moment, the evolution was in another direction. The four term, the four vector term. For example, not just m nabla m, but m 4 times, given 4 times, and again linear in special derivatives. Why it's so? Because it's more interesting, because when there is a linear term, that means that the polarization depends on the direction of rotation, clockwise or counterclockwise. So you can adjust even the direction of polarization. You can switch electric polarization by switching the cycloid from clockwise to counterclockwise. And of course, the second derivatives, I suppose that higher order terms, for example, magnetic exchange interaction. it's squared special derivatives, proportional to the square special derivatives. So it's another variant of high order term. And in fact, it's very, very, very strong. So I suppose that high order terms, you mean the second derivatives and so on, they're just neglected for simplicity reasons, because their contribution is not so high.
Thank you.
Okay. In this context, we can observe also the domain wall. The domain wall is a kind of fragment of the spin cycloid. So locally, the magnetization rotates, and there is special modulation of magnetization, and locally the symmetry is the inversion symmetry is broken. So domain wall can behave like an electrically polarized object. So the surface bound charges appears on the top side of the film, and the opposite sides, of course, on at the substrate side. But due to this electric polarization, they can be controlled by electric probe. For example, scanning probe probe of scanning microscopy, or just a pointed needle. Yeah, the wire. When you cut the wire, we can also have this very sharp ending. And you can see here, this is a conceptually simple experiment. When you apply voltage about hundreds of volts to this tip, you generate the high intensity electric field, high strength electric field, and you can control the domain walls. We can see here the domains, these bright stripes, and the gray stripes are the domain walls. And you can see here the electrode tip electrode, and when we apply electric field to it, the domain walls, the nearest domain wall attracts to the tip. And when we apply negative bias, the domain wall repel from the tip. So it's electrically controlled magnetic domain wall, just because locally it became ferroelectric, local multiferroicity in magnetic media, just at the domain wall. You can even modulate light from using this idea. You know, of course, that when the polarized analyzer are slightly uncrossed, there is a contrast, dark and bright contrast of domains, and when you apply electric field, you can move the domain walls like a shutter in the camera and modulate the focused optical beam. Another variant, since it's, the domain walls are polarized objects, you know that every dipole not only attracted to the pole, but it also orients, of course, like a needle of compass. Yeah, and in this way, the stripe domain in this form, the pet and to apply electric voltage, and this is stripe electrode. If it is directed along the domain wall, it orients the domain walls like this. We call it jalousie effect, due to the analogy to the blinder of jalousie curtain. And when we apply electric voltage, higher and higher, the image of the domain walls broaden. It's because just you can see here the domain walls in the spontaneous position is like this, and when you apply electric field, it inclines, and we can see it from the side, yeah, and its image broaden. And another very strong effect is generation, is a nucleation of the new domains. When you obtain the single domain state like this, it's homogeneous magnetic ordering, but when we apply electric field, the bubble appears. It is called bubble domain, and in its properties, it's also very similar to the soap bubble, because it tends to minimize its surface energy. When you switch off the electric field, like this, plus it disappears, it shrunk. So this bubble tries to minimize its surface energy, like a soap bubble.
Alexander, I see a question in the chat, so from Maxim Mazanov. Could the polarized domain walls be not only oriented, but also moved continuously by some special electric fields, perhaps alternating ones? So instead of changing the orientation, can you move them somehow in space?
Locally, you can move it like this, yeah. To find another equilibrium position in electric field. So its equilibrium position in spontaneous states is like this, yeah, and then in electric field, it can be moved. But when you are talking about the moving of all the ensemble of the main walls, it's a bit different. Because the equilibrium position are dictated by magnetostatic forces, and you should move all the domain walls. So it may be possible, but you need multiple electrodes and some kind of grid, or maybe the interdigit electrode system to transform it. And desirably, there should be some kind of defects to pin the domain walls to a new equilibrium position, so they can be transformed from one pinning site to another pinning site, like this. Because without this pinning site, it's a risk that there should be natural pinning site, and they be translated in an arbitrary way. Yeah.
Okay, thank you.
Well, the third idea, how to make the electric polarization from magnetization, from magnetic order, is comes from this picture, in fact. It is called three worlds. Again, it's a painting of Maurice Escher, and we can see here the underwater world. You can see here this fish. Our world, it can be found as a reflection in this pond. Yeah. And what is the third world? I suppose you know the answer. Yeah. It's a special phase of crystal. It's a surface of the crystal. The third world is just these leaves floating on the surface of the this bond, and the general idea, paraphrase the citation of Herbert Kramer, that it was called, that was coined in another context, of course. It was about diet lasers, but the idea is the same. The interface is the device. The interface have special properties. The inversion symmetry is broken on the surface, and you can convert magnetic media at the surface to magnetoelectric media. And the example of this is this spin cycloid in the monolayers of metal, magnetic metals. Of course, iron is not a multiferroic media, because it's a metal, a conductor, and you cannot even polarize it. But when you make the single monolayer of ferro, of course, electric field is not screened. And in this case, even in the absence of the external electric field, there is some effective field associated with the surface due to the broken bonds of the atoms. And the formalism just the same as for the multiferroic flexoelectricity term. It's again a polar vector. In this case, it's a normal to the field. And again, spin cycloid term here. Special derivative of magnetic vectors. And the magnetization, again, rotates. There is a special rotation of magnetization at the surface of these magnetic monolayers. It was predicted in the beginning of the century and was observed 5 years later. When we deal...
Sorry, Alexander, I had a question regarding the previous slide. So does this structure feature any unusual optical properties? So if they probe this by some light, do they see some interesting phenomena due to this special order?
In fact, the period of the structure is rather small, just several nanometers.
So much smaller than
the problem with resolution. Maybe at some oblique angle, yeah, when the light converts, maybe with a special prism that light converts to plasmon, or you can observe some interesting phenomena, because you need that the direction of the modulation should be along the pointing vector, or maybe wave vector in this case.
Yeah.
And in the normal reflection, I suppose there will be no effect.
Okay, thank
you. And of course, this structure have serious consequences on the magnon propagation. So you need some kind of excitation along wave excitation along the in-plane in wave excitation, plasmon, magnon, and so on. To observe these properties. Okay, so two-dimensional magnets is a rich playground for this magnetoelectric phenomena, and it became a special topic in 3 years. In fact, it's graphene-like. There are graphene-like media that possess magnetic properties, and due to this surface energy, due to this inversion symmetry breaking at the surface, they are at the same time multiferroics. So in Bilayer case, it looks like more symmetrical, but in fact, it provides another opportunity. the bilayer can be antiferromagnetically ordered. One layer down, for example, the bottom layer upward, and in the same way as in antiferromagnet, the antiferromagnetic vector was related to magnetic vector and electric polarization. In this case of vanadium sulfide, it also possesses electric polarization. In fact, its spontaneous state corresponds to some shift of the two layers with respect to each other. And when there is a mere light reflection transformation, I mean that the mirror reflection and the translation, the electric polarization can be switched with electric field. So when you switch electric polarization, the antiferromagnetic vector also switches. But how? What is the mechanism of this magnetoelectric interaction? Because electric polarization induces magnetic ordering switching. It's a kind of magnetoelectricity again. And in fact, in this case, it's a special ordering. Again, it was called something ferroelastic, ferroelectric, and in this case, it's ferro-valley. I mean that there is a special degree of freedom for collectivized electrons. It's not just their charge or their spin, but also this so-called valley. And the graphene-like materials, it is related, in fact, to this extremum in the electron structure. You can see here like a valley between the two mountains. Yeah, so it is called valley. It's in our usual speech we call it the top of valence band and the bottom of conduction band. And in fact, on the two sides of the beryllium zone, they can differ. They are not just the same for graphene-like material. It can be K plus and K minus value and valley, and they are characterized by special curvature. It's curvature, in fact, not in our space, it's curvature in the momentum space, the so-called Berry curvature, and some kind of another order parameter, ferro-valley, can be introduced as a difference of these Berry curvatures. It reminds me antiferromagnetic vector, in fact. There are two Berry curvatures, and you obtain difference between them. And when there is a time inversion symmetry, you convert these Berry curvatures, just accept the magnetic field, they change their sign, and in this way, this ferro-valley is another order parameter that is a mediator, a bridge between magnetic order parameter, antiferromagnetic vector, and electric order parameter. The physics is even more rich in this case because of the special degree of freedom of collectivized electron, Bloch electrons.
And so regarding this part, I wonder if it is possible by applying external electric field, close band gap in one of the valleys, still keeping open a band gap.
Close it.
Yes.
I suppose it's still dielectric. Well, in fact, our colleague calculated it, Chinese colleagues, and there was special note from them that when they apply extra high electric field, they transform the this structure from dielectrics to metal. So maybe what you mean, or at least maybe Fermi layer transpass this the variance band.
Yeah.
And as a rule, the transition from dielectric to metal implies that it's not antiferromagnetic anymore, it became ferromagnet. And they also, my colleagues also confirmed it.
Very interesting, thanks.
It's a quite recent paper, 2 years later, but it's still reason because the topic, it's a topical question, these 2D magnets. Well, and finally, this idea reminds me the idea of Lego. You can construct composite material from magnetic dielectrics and ferroelectric dielectrics and make an artificial magnetoelectrics. Due to the mechanical coupling, when you apply magnetic field, and due to the magnetostriction, the magnetic layer transforms, deform, and it deforms also ferroelectric layers, and due to the piezoelectric effect, you can obtain electric polarization. This is the general idea of composite, magnetoelectric composite. And in 2D case, it's also possible, for example, this paper of Japanese scientists, they have this Lego scheme for some perovskite, niobium something. I forget, but I can consult it with. It's not so important. The idea is just you combine ferroelectric field, ferroelectric film and magnetic film, 2D materials, and they attach to each other due to van der Waals forces without any glue. Well, and this is interesting in the context of special branch of electronics that is called Straintronics. Straintronics is it follows from its name that it's based on the strain. When you deform electric media, ferroelectric media, you obtain by this electric effect some electric field, and it can change the magnetic state of the structure. So it's kind of magnetic memory that is switched by electric means, but the mediator, the agent between them, is a straintronics. And it is very attractive due to this unprecedented, uniquely low switching energy. It's about 1 joule, and in the context of big data, blockchain, and that in 10 years that the power we need 50% of power, global power, for calculation. It's very interesting, this is Straintronics. And coming back to the beginning of our talk, I mentioned Bernard-Tillingen composite media. Do you remember this engine oil and particles rotating in it? In fact, this idea waited half a century to being realized. It was implemented only with the advent of the electronic ink. So, for example, this so-called Giricon particle with black and white semisphere. It's kind of ink, electronic ink in electronic books. But when you mix the magnetic particle in it, you can polarize it in electric field and make a special composite magnetoelectric media. Very simple, very similar to the original Bernard-Tillingen idea. And in this context, it reminds me another idea of Paul Ehrlich, Nobel laureate. He shared the Nobel Prize with Mechnikov. In fact, they were strongly opponents to each other. Mechnikov defied the humoral immunity concept about these anti-gens and so on, and said that there are special cells that eat the bacteria. But in fact, immunity is the whole system, and both of them were right, and they shared this Nobel Prize. It's again very usual situation in the physics. But Paul Ehrlich proposed this so-called magic bullet concept, that there should be special drug that target the cells, the damaged cells, and not target the healthy ones. And the magnetic nanoparticles can be such a magic bullet. They can be introduced via intravenous administration to the body and then circulate due to the blood circulating, and they can be accumulated at the damaged area, and then you can apply, for example, alternating magnetic field to hit them, but they can also be magnetoelectric one. For example, this particle, it has magnetic core and ferroelectric shell. And when you apply magnetic field that penetrates through our body without any damage and without any screening, when you apply magnetic field, locally on the particle, electric field appears, and it can be used to release the drug that is glued to these particles, or even electroporate the membrane of the cell. You can fracture the cell membrane with electric field, just like a breakthrough in dielectrics. And futuristic and maybe a bit terrifying promise of these magnetoelectric particles is their usage in the neurophysiology. They can cross the blood-brain barrier and distribute in the brain. And if they are, as soon as they are magnetoelectrics, the electrical activity in our brains can induce some magnetic changes of magnetic state of these particles that can be mapped with usual magnetic particle imaging means. It's just like a tomography, magnetic tomography, and vice versa. By magnetic field, you can stimulate the electrical activity of the brain. So with it, I want to finish my report and again repeat these three senses: how to make the electric ordering from the magnetic ordering. Three general ideas: antiferromagnetic ordering, special modulations, and interface-related phenomena. Thank you for your attention.
Thanks a lot, Alexander. Very instructive talk. So I personally learned a lot from it. So now it's time for questions, colleagues. If you have any, please raise your hands. So in the meantime, I'll start with the first question. So the very basic one. So I wonder how people do the calculation of this magnetoelectric susceptibility, which you just showed us on the first slide. What are the theoretical approaches used in the literature?
Mm-hmm. Usually it's a group symmetry analysis.
Yes, but then if I want a numerical value of this alpha ME, let's say, can I calculate it theoretically?
You can calculate it from the microscopic means, just by taking into account the shift of the ligand ions between two magnetic materials. You can see it's just an oxide. There are two magnetic ions and a ligand between them. Usually it's oxygen, and slight deflection of ligand from the symmetry position between them leads to the nonlinear ordering of magnetization. So you can find from this ab initio method how magnetic vector react on the shifting of the ions due to the electric polarization. It's a microscopic approach. And so there is also, yeah.
So it's general like ab initio methods like DFT, and then people calculate these positions of the ions equilibrium, and from that they deduce this electromagnetic response.
Yeah. It's ab initio method. And in our tradition, more usual to use the space group symmetry approach, the phenomenological, coming back to the Landau school, yeah, and we can analyze the transformation properties of magnetic vectors, antiferromagnetic vectors, electric vectors, and combine special invariants from them. And in this case, you can make some, you can reconstruct the matrix of magnetoelectric effect. You can see here, for example, these are diagonal terms that are proportional to the antiferromagnetic vector component along the principal axis. So you can, of course, by phenomenological approach, you cannot find exact numbers of A1 and A2, but you can reconstruct the form of the magnetoelectric tensor.
And so this paper in GTP letters is just discussing these details, yeah? So just to... So
yeah, it is a classical paper that deals with the switching of antiferromagnetic vector and switching the magnetoelectric tensor. You can see here the diagonal term in this phase and non-diagonal terms in special magnetic field induced phase.
Right, good. And then another question. So you were discussing the concept of magnetoelectric Lego. So people are combining different layers, and by means of that, they are tailoring magnetoelectric response. So I wonder if there are some studies, let's say, on enhancement, achieving maximal possible magnetoelectric effect. So are there any recipes? What should we do to get maximal magnetoelectricity?
Yeah, the main problem here, I suppose, is clamping to the substrate. So this field somehow should be fixed, and usually it is fixed by the substrate, and substrate prevents from the deformation. But the recipe for it is to make some kind of columns of one phase in the matrix of the another phase. You see, when you apply, for example, heteroepitaxy, there is a substrate, you deposit some, for example, ferroelectric media, ferroelectric compound, and magnetic compound. And it depends on the direction of the substrate. For example, 0, 0, 1 or 1, 1, 1. It depends what happens to these compounds. Some compounds can have low surface energy, smudgewood. They form matrix, and the other one have drop-like configuration. They form nanopillars. So in this case, you form special structure with nanopillars of, for example, ferroelectric phase and magnetic matrix. And when you apply electric field, nanopillars can be stretched like strings. It's much easier due to the reduced clamping to the substrate. it's much easier then to deformate. So in this case, the magnetoelectric effect can be enhanced in the composite.
Interesting, thank you. And then another question, I was wondering what are the maximal values of magnetoelectric effect achieved currently? Of course, we saw your review, but it's like 10 years ago, but now it's maybe some other record values are achieved. So.
In fact, they are not so high. You can see here the table of it. But for composites, for artificial multiferroics, their values can be several orders higher than in classical chromium oxide. Chromium oxide, for example, in technical units, 20 millivolts per centimeter Ørsted. And in the case of composite, and in the case of resonance, you can vibrate it, yeah, and due to the proper frequency, when you apply frequency close to the proper frequency of the structure, there's a kind of resonance, and you can obtain up to volts or even tens of volts when you apply Ørsted field.
Right. Thank you. So there is a question from the chat also. Since there appears to be some torque on magnetic structure when electric field is on in multiferroics, are the antiferromagnetic resonance features altered by electric field?
Yes, I suppose in multiferroics, the frequency of antiferromagnetic resonance can be controlled by electric field that can be shifted. It's usual methods to obtain the magnetic coefficient.
Okay, good, thank you. And then maybe the last but not the least question. So in the very end of your talk, you mentioned that there is a possibility to use these magnetoelectric particles to control either to control brain or to image the neural activity in the brain. So can you elaborate on that a little bit more? Are there any experiments on that kind, or it's just purely simulations so far?
Yeah, for mapping up to date, it's simulations. For control, there are in vivo experiments on mice.
Yeah, it's interesting because I was listening recently to a seminar from a guy from medicine. He was talking about different approaches to explore the neural activity of the brain. So there are different techniques, but this is a novel one. So it's not clear. Maybe it will provide further advantages in understanding.
Even optogenetics, that kind of thing. Photonics.
He was a clinician. He was describing different techniques like MRI. So those which are used currently in the medicine, but this technique is a new one. So
it's quite new.
Yeah, very interesting. Thank you so much. So I do not see other questions from the audience. At any case, maybe if we will have further questions, we will just email you, because this field is very new for us. And from the today discussion, I got several very nice new things which I previously didn't know. So thank you, Alexander, for coming. And so see you. yeah. So and see you. I mean, the rest of the audience next week. So we will have a seminar by Professor Schwetz on high-order topological states. So he's visiting us virtually from the United States. So the seminar will be in the evening, 5 p.m. Moscow time. So stay with us and see you. Goodbye.
Bye-bye. Thank you again.
Thanks a lot.
For this opportunity.